In my last video, I introduced my system for painting the textures of 3D models using traditional methods, specifically oil paint, which I would recommend watching before this one. In that video, I painted this model of a skull, which appears to be lit because the light and shadow on the skull were painted directly into the texture itself. This method produces a really good effect when we assume that the painted objects and the lights will never move, which is the case if we are just showcasing a model. However, what happens if we try to change the lighting setup or the model position? Well, nothing. Since the lighting is included in the texture, we can't change it at all once the painting is complete. Well, this is a bit disappointing. My fun new method isn't practical at all for people who want to make any sort of dynamically lit animation or game using traditionally painted assets. I'd like to be capable of producing more than just model showcases using traditional methods, but I don't want to be stuck just creating objects with no distinct lighting. This is a fine method which is used in plenty of hand-painted projects, but I'd like to do something a little more interesting. I guess I'm going to need to put some work into dynamically lighting my hand-painted models. First things first though, how does everyone else do it? In real life, when we turn on a light bulb, it will emit light rays in all directions. These rays bounce around, interacting with objects they collide with, and eventually they might make their way into your eyes, allowing you to see the objects that reflected them. The more light rays which bounce off a given object and into your eyes, the brighter the object will appear. If no light rays bounce off the object, or if the light rays don't reach our eyes, we can't see it. The process of creating these rays and simulating their paths is known as ray tracing. It seems like a simple enough concept, so surely that's the best way to light 3D models. Well, yes, a physically accurate model is always the best. Unfortunately, in 3D graphics, we've sort of only just started having the computing power to calculate the paths of enough individual light rays to construct a good image in a real-time setting. Ray tracing is beginning to appear in games. You've probably seen plenty of RTX comparisons, but it's still a relatively young method, and we need a lot of filtering to make a good image because the base frames are very noisy. In fact, even the earliest examples of pre-rendered movies produced using ray tracing didn't appear until the mid-2000s. This sort of begs the question, what were we doing before? The answer is that it's just sort of always been a trick. Instead of accurately simulating light, we employ a range of techniques to fake it. There's an incredibly broad spectrum of these tricks, but for this video I'll discuss only the most simplified lighting methods. We'll even ignore that objects cast shadows on each other, since creating shadows is actually surprisingly difficult and would probably be a separate video on its own. In my last video I described how objects are constructed using a large collection of separate triangles, or triangular images. But for the moment let's ignore most of them and consider only a single triangle. Previously I represented these triangles as solid objects, like paper cutouts, but in reality we usually treat them more like a one-way mirror. If we look at them from one side we can see the image, but looking from the other side we see right through them. By constructing a model so that only the outside surface is visible, we stop ourselves from wasting effort by drawing the inside surface as well. This basic optimization can also help us understand how we calculate the lighting on a triangle. We construct a simplified lighting example. Here is a light source which sends out rays of light in all directions, and here is the triangle which we want to light. To make it clear which side is opaque, I'll draw this arrow which points out of the visible side at a 90-degree angle. If the arrow is pointing towards us, we can see the triangle, and if it points away, we cannot. This arrow is commonly referred to as the normal vector, which we consider constant across the entire triangle, such that no matter where we place it, it always points in the same direction. In this model, let's ignore any light bouncing, and just consider that the colour of the triangle is equal to the number of rays that hit it. If the maximum number of rays hit it, then it's white, and if no rays hit it, then it's black. Now if we move this triangle around, we can see how its position affects its brightness. The closer it is to the light, the more rays will hit it, and the brighter it becomes. This dimming with distance is observed in real life, and is well described by the inverse square fall-off curve. Similarly, if we rotate the triangle, we see that the most rays will hit the triangle when the normal is pointing towards the light source, and that the number of rays reduces as it begins to rotate. When the normal begins pointing away from the light source, all light passes through the triangle because it's transparent on that side, so it becomes completely unlit. We also see this effect in real life. Surfaces pointing towards a light are brighter than those that slope away, and surfaces on the opposite side of an object to a light are unlit. This model seems to do a pretty good job of lighting our triangle. But Bobber, I hear you cry, isn't this just more basic ray tracing? Well, yes, we are still tracing light rays, which is not ideal. Let's try to simplify it further. The first observation is that we are ignoring shadows, so we don't care about rays which don't hit the triangle. We're just wasting effort producing them, so we should only create rays which will hit the triangle. What if instead of drawing all of the rays coming out of the light, we draw an arrow from a point on the triangle to the light source? We can guarantee that a ray which travels from the source along this arrow in the opposite direction will hit the triangle at the origin point, so we call this arrow the light vector. By calculating the length of this line, we can tell exactly how far away that point is from the light, meaning that we can calculate the brightness using the inverse square fall-off curve we saw before. Similarly, we know from before that if this light vector is pointing in the same direction as the normal, then the point will be maximally bright, and that as the angle increases between the arrow and the normal, the brightness of the point reduces, until the angle is greater than 90 degrees, at which point the brightness is 0. One of the simplest models describing the relationship between this angle and the light brightness is the Lambertian model, which just considers the brightness as the cosine of the angle if it's less than 90 degrees, and 0 otherwise. You'll notice that we've now recreated the effect of a more physical model using only 2 rays, and modelled the brightness of the triangle based on only 2 values, a distance and an angle. This calculation is very easy and very cheap, so much so that instead of performing it once per triangle, we can perform it for every pixel of the triangle on the screen, to represent how the brightness changes across its surface. Since this lighting doesn't depend on anything other than the triangle and the light position, we can draw each lit triangle independently, and then put them together to reconstruct our model without worrying about any complex interactions between triangles. Oh, seems like we've actually constructed a pretty decently lit model. However, you may notice one issue. It's really obvious where each of the triangles are, since there are very harsh changes in lighting between them. This is because we've considered that the normal vector is constant across the entire surface of each triangle, meaning that as we move from one triangle to another, the angle between the light and normal vectors changes suddenly. If we wanted the object to look smooth, then we would need the difference between these normal vectors to be smaller, so there's less of a harsh lighting change. We could just increase the number of triangles in the model and make the geometry smoother, since eventually each one becomes small enough that the difference between their normal vectors is tiny. This isn't ideal though, since if we needed multiple smooth objects, we could quickly get into the multiple millions of triangles rendered and significantly reduce the performance of our render engine. Instead, we need some other way of changing the direction of the normal vector for each point along a triangle to make the transitions smoother. Of course, it's possible to do this by modifying our light calculation. The simplest of these methods is to only set the normal vector at each intersection between corners and then blend between them across the surface of the triangle. This method makes the model look smoother, but can we go further? In my previous video, I discussed how we can use images in place of triangles to dramatically increase the color detail across a triangle. Is it possible for us to do the same with normal vectors to increase the detail in our lighting? The answer is yes, but it's a bit more complicated. The most fundamental concept for creating an image which maps normal vectors onto triangles, typically called a normal map, is that in our calculations we describe each vector using a single 3D coordinate. Similarly to how the corners of each triangle are described by 3 different values, the position of the corner along the x, y, and z dimensions, we can describe the direction of an arrow by placing its base at the 0, 0, 0 point and storing the x, y, and z values of the end point of the arrow. For simplicity, we assume that the normal vector has a fixed length of 1, meaning that each of the x, y, and z values falls between -1 and 1, regardless of the direction the normal points in. The point is that to describe the direction of any normal with an image, we need to be able to store 3 values between -1 and 1 for each pixel. Fortunately, conventional images already describe 3 values for each pixel, being the proportion of red, green, and blue found in the color of that pixel. In graphics, these values typically range from 0 to 1, since there isn't really such a thing as a negative color, but we can easily convert a value between 0 and 1 to fall between -1 and 1 by simple arithmetic. It is therefore simple to see how the color of a pixel can be used to describe the normal vector at that pixel instead of an actual color, by acting as if each color value instead describes the vector value along each axis. Using this method, we can now describe the normal vector at each point on the model, just the same as we used a regular image to describe the color at each point on the model. The most significant implication of using a normal map instead of a more basic smoothing method is that by deliberately modifying the normal vectors, we can make the model appear to be a more complex shape than the actual triangles describe. As a point of clarification, there are actually multiple ways to define normal vectors, with the main ones being called object space and tangent space mapping. The only difference between these methods is that when lighting models with the object space map, we use the normals of the map directly, whereas with a tangent space map, we rotate the map normals relative to the triangle they're displayed on. In this video, I'll show you object space maps because they're much easier to interpret, but behind the scenes I'll be converting to tangent space maps since they are better for lighting objects with symmetry or moving parts. Hopefully now you know the basic principle of how normal mapping works. We've arrived at the main question of this video. How can we make interesting normal maps for painted objects? For the purposes of this exploration, I've made a seaplane based on some plans I found for a model Aeronca sedan. First I'll need to paint it so there's no lighting in the texture, instead focusing on just capturing the colours of the model if it were uniformly lit. To the app. There, now we have something to work with. At the moment it's still just an unlit model like the last one, so let's get to work on making this model work with dynamic lighting. The most basic option is to just generate a smoothing normal map by blending between the triangle corner normals as I mentioned before. The result looks like this, and is generated automatically from the model when we add a normal channel in the app. The result is a model which appears lit, and which reacts to dynamic changes in the lighting, so I guess problem solved. I don't think this is really a good option though. Is it lit? Yes. Does it look any good? No. I think I'll need to do a bit more work. The obvious next step is to paint the normal map the same as I hand painted the regular colours. It makes sense that if I want normals which match the hand painted style, I should just paint them as well. I've added functionality to my app to enable me to paint normal maps with real-time updating lighting, as well as the option to just look at the painted normal map as a regular colour image. I guess it's time to sit down for another few hours of painting. Well, this painted normal looks quite good if we use it as a colour texture. Let's just switch to using it as the normal map. Oh, this doesn't look very good. The lighting on the model doesn't seem to match the position of the light. What's gone wrong here? Remember how before I said that these colours represent exact mathematical values? Unfortunately, that's not really how we see colour at all. A colour which has double the green of another does not appear exactly twice as green to us, but it would to a computer. This means that it's very difficult to even perceive the exact colours of a normal map, let alone mix them with paint to a high enough accuracy that the vectors are even pointing in the right direction. Here is my painted map compared to the generated map, which I used as a reference. They both appear to be roughly the same colours to the human eye. However, if I split the colours of my painted map the same way as I split up the generated one, they don't both have the same gradients of red, green and blue. This means that my painted vectors are not physically correct for the model, so the lighting is incorrectly calculated. Because of the very distinct difference between how I see colour and how a computer does, it seems that manually making the normal maps with traditional methods might be more trouble than it's worth. There's another problem which we can see if the diffuse map is applied as well as the normal. The brush strokes in the diffuse don't match up with the strokes in the lighting calculation, leading to a strange broken up effect which makes it more difficult to see the details in the painted diffuse. Back to square one, I guess. It is undeniable, however, that the painted map creates an interesting effect by lighting individual brushstrokes differently. If we could somehow find a way of replicating this effect with accurate normals, then we might be onto something. While we're at it, it would be nice to make the brushstrokes in the normal map match up to the shape of the brushstrokes in the diffuse. As it happens, I've solved both of these problems. I've designed an algorithm which takes a painted texture and its model and then generates a normal map which has the individual stroke lighting effect, but also which matches up with the painted map. The aim is to make the model appear as if the lit brushstrokes were simply painted to match up with the lighting. I'll try not to get too much into the details about how the algorithm works. The essential principle is that we measure the rate of colour change at each pixel in the diffuse map. Areas with low colour change are likely to be brushstrokes, and areas with high colour change are the borders between colours. We find the average normal vector in each isolated area of the image with low colour change, and set every pixel in that area of the map to the average value. Then we blend the colours between separate adjacent brushstroke areas to fill the gaps. I've designed this algorithm to run on the GPU, meaning that the process can be performed within a few seconds. This is fast enough that we can perform real-time modification of parameters in the application. This allows us to create a range of map types, from very noisy, more smoothly lit textured ones to maps with very large, clearly separated brush surfaces. Here is my C-plane lit with a few different configurations I made earlier. Okay, now we have a nice tool for generating normal maps which appear to light brushstrokes individually. Why is there still time left in the video? Aren't we done? Well, not quite. There's one more thing I'd like to try. One of the main advantages of using traditional methods to do my texturing instead of painting digitally is that the diffuse map physically exists and has a textured surface in the real world. This surface detail appears in the scanned diffuse texture. Because the light is displaced from the scanner camera, we will see highlights and shadows in the image relative to the position of the light and to the detail on the surface. This means that the diffuse texture inherently has some light and shadow detail, even though it's supposed to only represent flat colour. Is there any way for us to pull this surface texture from the real world into the digital render, so that the highlights and shadows in the diffuse react to the moving light? As it happens, there is. Photometric stereo is a technique which has existed since 1980, in which we attempt to calculate the normal vectors of a real object using a set of photographs with different lighting setups. Assuming that we have enough images of a subject, and that we know the position of the light in each image, it's theoretically possible to create a normal map which replicates the lighting of the object. The basis for this method is relatively simple to understand. Imagine that we have two photos of the same object taken from exactly the same position. In one photo we know that the light is on the left of the object, and in the other photo we know that the light is on the right. Therefore, if we compare both images and find that a pixel in the left lit image is brighter than in the right lit image, then we can assume that the normal vector of that point on the model is facing more towards the left light than the right one, or that if the colours are similar, it's somewhere between them. If we then take two more photos of the object, this time lit from the top and the bottom, we can similarly determine if the pixel is lit by a light from above or below, to calculate if the normal at that point is pointing more up or down. In theory, by repeating this process enough times with the light in enough different positions, we would eventually be able to perfectly predict the normal vector at each pixel of the image, and create an accurate normal map image. From this, we could simulate what the object looks like in a range of lighting conditions using only a flat plane model. Performing photometric stereo on a painting is no different. I use a photoscanner to take high-resolution images of my paintings, and the photoscanner has a fixed light position relative to each point in the image. This means that it's very easy to simply take a lot of scans of the painting, rotated at different angles on the scanner, to capture images with multiple known light positions. I've implemented a photometric stereo system into the app, which lets me extract the normal vectors of the physical painting. Here is a 3D render of the diffuse painting of this piece with the scanned map applied. This system also gives me an opportunity to solve an issue some people have had with my hand-painted models in the past, by generating an improved color map, an albedo map. This is essentially the same as a diffuse map, but without any highlights or shadows, so there's no obvious physical detail. Given an accurate map of the normal vectors in an image, I can approximate the albedo color of each pixel in the map just by taking a weighted average of the pixel colors in all the photo scans. Pixels that are brightly lit or entirely shadowed have a much smaller weight than the same pixels in images where the light is more neutrally placed. The result is a map which describes all the same color information as the old diffuse, but with no highlights creating effects like the canvas texture. This lets me either entirely remove these details from my models, or by combining the albedo and the normal, it lets me render a more physically accurate painting with surface details that react to light. Once I've generated the photometric stereo normal map, it's easy to wrap the map around the 3D model, meaning that the canvas details now influence the lighting of the C-plane. This also produces quite a cool effect, making the rendered object look more like a physical model which has been constructed by cutting out and folding up a canvas. This method can also be combined with the algorithmic normal generation to produce some more interesting effects. We could use the albedo map with the flattened brushstroke normals to produce an object which looks quite unphysical. We can also try mixing the stroke averaged normal with the surface detail normal to create a model which appears as if it were made of a collection of separate physical brushstrokes floating in space. In this video, I've introduced a few different methods for performing dynamic lighting on my hand-painted objects. I'm not sure that any of these techniques can completely replace the effect of painting light by hand, but it opens up more opportunities for the types of models I can create. It's easy to imagine that we could have some animation where the background doesn't need to move, so could have hand-painted lighting, but the subject does need to move, and so would take on one of the lighting models. As with all technical problems, I think that there are different situations where each method comes into its own. Which of these methods do you personally like the most? How would you use it? As before, you can go and try out the app for yourself. It's open source, so you can go and look under the hood, or if you don't care about that, I have an up-to-date pre-built file which you should be able to download and run that contains tools to do everything I've talked about today. I'll include a link in the description to the GitHub repo. If you'd like to see more short-form content or some making of videos for this video, you can go and check out my shorter videos on Instagram or TikTok. If you're interested in any of my other artwork, you can also go and check out my website, which has a gallery of my past paintings and 3D models. Thank you for watching this video all the way through. I hope that you enjoyed hearing about my work on this project, and that you stick around to see what I do in the future.